Okay, so hello everybody. Welcome to the Arena Institute for Computing at Boston University. The Artificial Intelligence Research Initiative is one of the Arena Institute for Computing initiative, and the Distinguished Speaker Series, it's a series of talks that is aimed to a broad audience, both internally and externally to Boston University. And we welcome researchers that are renowned nationally for their work in artificial intelligence. This is basically the agenda for today. We already had our reception, and this is the welcome. And Samory will give us a talk around 40-50 minutes, and then we will have some time for the questions. Now, if you do have questions, please go directly to the Microsoft there in the center of the room and just ask your question. Let me also introduce you our upcoming speakers that we will have both in the spring and fall semester. We will have Rogerio Harris, Principal Scientist and Manager at MIT IBM Watson AI Lab. Csaba Szeveszpari from the University of Alberta, and Asha Wilson from MIT. Now, let me introduce you Samory. Samory is an associate professor in statistics at Columbia University. He got his PhD from USCD, advised by Sanjoy Dasgupta, and then he did a postdoc at Max Planck Institute, advised by Ulrike von Luxemburg and Bernard Shelkoff. And then after that, he held positions at TTIC, Princeton University, and a recent visiting position at the Institute for Advanced Study in Princeton. His work has been recognized by various honors. For example, the Bell Lab First Prize, the Sloan Fellowship, and he is an associate editor for the Journal of Machine Learning Research, the SciAM Journal of Mathematics and Data Science, and he was the program co-chair for the Conference on Learning Theory in 2021. Now, before we get started, let me also remind you to subscribe to all the channels that we have for the Arena Institute so that you can be updated on all the initiatives that we have. And that's it. And let's welcome Samory here at Boston University.
All right. Okay. I hope the microphone is working. Everybody can hear me well. So first, thanks for having me. For me, it's an honor to be here. The last time I was at BU was maybe 10 years ago, something like that. And I came back. Everything is huge. I see buildings everywhere. It's beautiful. So I'll be talking about transfer learning and, in fact, and multitask learning. I'll define all these terms as we go. And this work was first started with Guillaume Martinet. And there we were looking at the non-parametric setting. All I'll be talking about will be classification. And I'll define in a second what I mean by non-parametric setting and such. And, but what I'll be talking about is current and ongoing work with Steve Haneke. And it's mostly on the parametric setting. But much of the intuition started with the work with Guillaume Martinet. All right, so what do we mean by transfer? I'll just quickly say high level. We have a distribution queue on which we want to do well. However, we have data, a lot of data from a different distribution, and maybe a little bit of data from the distribution queue itself, right? And so what motivates it? In the most basic situation that a lot of people study, it's this case here. I have labeled data from P, and I want to produce a good classifier for Q. Okay, And often, it's assumed that I only have data from P. The type of motivation, I'll use Apple series as a motivation. So imagine back in the days when Apple Siri first came out, it was mostly trained on American English speakers, right? Then they sent it out to the real world, and people like me with an accent could not be recognized by Apple Siri. In fact, some people throughout the world still cannot be understood by Siri. And what did they have to do? The default sort of was to go back and acquire a lot of representative data. Okay, so the key issue that we'll be discussing is the fact that often the data that is representative of the population or distribution that you're trying to do well on is not available. And you have a lot of much cheaper data from a different but related distribution. Okay. So the point of transfer is exactly that. We do know that we have some information in the American English speakers about every other accent. What is that information, and how do we transfer that information cheaply without having to throw away the last data and reacquire too much data? We want to acquire as little data as possible, keep the cost cheap. I hope that that's clear. And it's not only about how much data do we acquire. What is the set of procedures? There are tons of procedures out there for transfer learning. What is the set of procedures that are doing something optimal? What is the best we can do to retool, to refit our algorithms? Okay. So that's the main goal, cheaply transfer machine learning software between populations. One second. Yeah, so cheaply transfer machine learning software between related populations. And by cheaply, again, I'll reiterate, not only in terms of data, the amount of data, but in terms also of the tools that we're using. So both sort of come into play. So this problem is of general relevance because the key problem is the fact that, again, we have mostly data from a population, but we want to do much better. We want to do well on a related population. And so you can imagine AI for judicial systems. The source population tends to be prison inmates, and this is a biased population with respect to everybody that might get into the whole judicial system, right? So that's the target population. And in fact, we do know that we have a lot of inaccuracies in the current models for these type of problems. This issue is almost everywhere. You can imagine medicine. You only have data from particular people who are in the hospital system, but you want data about the general population. All right, so the problem's been around, and people have been looking at it forever. Right, and so there are many different procedures that have been proposed to address it. And theoreticians have also been looking at the problem for a long time. However, we all know that often it is the case that theory needs to always catch up to practice. Right, we're still trying to understand the principles of transfer learning. So here are some of the basic questions that just come from applications that we actually, theory, still cannot fully answer. So suppose H hat is a classifier that is trained on source data, P. I'll keep calling the training data the source data, and the target data or target distribution, I'll be saying source and target, and I hope that's clear. So H hat is trained on source data P to be transferred to the target Q. A first question that a practitioner might ask, do I have enough information in my data, in my source P about the target Q? What do we even mean by information, right? Next, if I do have some information, or if I don't have enough information, how much new data should I acquire, depending on the level of information I actually have? And what is that level of information? How much data, how does the amount of data relate to that level of information? Would unlabeled data help? The question here, would unlabeled data help? We know that unlabeled data is often cheaper. If you think about computer vision, for instance, we have a lot of images. We don't, labeling is the expensive part. And what's the right mix of P and Q? Given particular sampling cost. What I'm referring to here is, imagine Google. Google want to build software for a particular problem. Maybe it's computer vision. Maybe it's self-driving cars in Boston. And however, it's much cheaper for them to acquire data from Nairobi, let's say, right? And acquire some data from New York. For some reason, it probably will be more expensive. But you have different cost of data. And you want to say, you want to answer a priori, which data should I buy? I hope that that's sort of clear. Or what's the right mix of data from the different, depending on the cost and depending on the performance or accuracy that I want to achieve. So those are basic questions that we are not there yet. We don't know how to answer yet, right? And so part of the talk will be to try and start answering some of these questions. Fine? So altogether, these questions just boil down to what is the relative statistical value of data from P with respect to data from Q. Okay? And we know it depends on how far P is from Q. And what do we mean by how far? That's sort of the main question. What do we mean by how far? How far is how much information is P in Q, is in P about Q? And what is that notion, that right notion of distance, quote unquote distance between P and Q? And so much of what I'll first talk about will be that. What is that right notion? That sort of captures the limit of transferability and helps answer these questions. All right, so how do we proceed? First, as I said earlier, much of the earlier work that we did was in the non-parametric setting. And by non-parametric setting, I just mean that we are in classification where we don't make too many assumptions about the eventual best classifier for our problem, right? We allow it to be nearly anything. But what we'll talk about today will be mostly the case where we assume that the classifier, or the best classifier, comes from a particular set of classifiers, or a good classifier comes from a particular set of classifiers. So here, covariance shift was the first work with Guillaume Martinet. In covariance shift, we assume, again, we're in classification, we have X, we have Y. We assume that the main thing that has changed is the marginal PX has changed between P and Q. In posterior drift, we assume the reverse, that is the conditional P of Y given X that has changed, right? And so this is work by Scott, Kai and Wei, and various other follow-up work. Recently, there is a new paper recently by Reeve Cunnings and Richard Samworth that tries to combine intuition from these two, okay? And that question is still there. Can we come up with a notion that fully combines PXY and QXY, right? So here again, the main thing we will look at is VC classes, and I'm calling this parametric, and all I mean here is bounded VC classes. Bounded VC classes could be my choice of, my simple choice of procedures. Maybe I'm only looking at linear classifiers. Maybe I'm only looking at random forests. Maybe I'm only looking at neural networks, etc. There is some question as to whether these algorithms that I just, this family of algorithms that I just said are really parametric or non-parametric. We'll let that go. We'll assume that they are parametric and they are bounded VC classes. Surely they are parametric if I assume, for instance, a fixed size neural network as sample size is growing. Okay. Does that all make sense to everyone? For those who don't know VC classes, it doesn't matter. All we mean here is a notion of complexity of my procedure, of my class, okay? And we need to control complexity in order to control variance, all right? Okay, so again, we are given source data, label source data from P, the source, and label target data from Q. This is a bit of a change from what people used to, how theoreticians used to look at the problem. Theoreticians used to, as I said earlier, used to just assume that NQ, the number of points from the target, is 0. And they just have a lot of source data. However, that, to me, was one of the main issues in trying to understand transfer, because by not looking at this sort of setting, this sort of setup, it was hard to sort of understand if a classifier is given data from both, which one is giving most information? What is the relative value? And so here we want to look at both together and try to give rates of convergence in terms of both sample sizes together and understand the apport of every sample size into the rate. I hope that's clear. So The goal is classification error, minimizing classification error. We are going to look at this object, the excess risk, in classification with respect to the best excess risk in the class. Okay? And the basic question becomes, which excess risk do we achieve in terms of NP and NQ? What is the best excess risk achievable in terms of NP and NQ, given some notion of distance, and which notion of distance should we be using? And we want to understand the limit of transfer, and not only the limit of transfer, but which algorithms attain this limit, and under what situation. How much information do the algorithms need to know about the distances in order to attain this limit? So those are the type of questions we want to understand. Fine? Also, please interrupt me anytime if there is some clarification question. We don't have to wait till the end. So, all right. So, go ahead. Yeah. Let me go back.
So, like, no, just
I don't know how to use this thing. Yeah.
when you say the notion, like, presumably the learning algorithm is not tailored to P and Q, otherwise it wouldn't be in the data.
Yeah.
So, what am I assuming about the?
So we'll
What
like.
does the algorithm know about P and Q going in?
So we'll go through all that. Okay, so those are the different questions we'll be asking. Is what if the algorithm knows this? What if the algorithm does not know this? What are the rates achievable? And how does the distance between P and Q depend on the algorithm? Does that make sense? All right. So first, let's talk about what people have done, what notions of distances have been used. And notions of distances have come up for about 10 years. Theoreticians have first been looking at essentially all existing notion of distance between distributions, right? And then the most prevalent ones are the ones I'm going to go through first. Extensions of total variation, are the ones that theoreticians look at the most. And here, I'll keep using this cartoon. In this cartoon here, this is the source distribution, and this is the target distribution. It's a distribution over object. These are the classes. And the target distribution shifts mass to this area for this particular object, okay? So very simple cartoon. Imagine this being all accent from all English accent from the US, and these being all English accents from England. And here there is a lot more Scottish accent, let's say, okay? So the type of result that was obtained in these cases, let's consider extensions of total variation. Extension of total variation, all we mean is we're looking at the difference in mass assigned by P and Q to regions of the space, okay? Total variation will be the difference in mass over all possible measurable regions of the space. And to sort of start answering your question, what these notions, dA divergence, Y discrepancy, and all them are doing is just looking at only those regions of space that are essential under my classifier. So if I'm looking at linear classifiers, I would only look at the regions of space where two linear classifiers disagree. Those are the only essential regions because that's the only thing that makes a difference in their error. Make sense to everyone? Okay, and so it's tailored to the classification procedure, these notions, and that was actually a first nice insight that one should not just be looking at general measures of discrepancy, but should tailor it to the algorithm in some sense. So, however, this is the issue that we quickly saw here, is that the type of excess risk that they could show has a term that goes down to 0 as sample size increases. And again, I'll repeat here that they only looked at the situation where we have no samples from the target, and so as the source sample size increases, plus the distance between the two distributions. And this gives the impression that we can never drive the excess risk to 0, which is sort of what we know in simple passive learning, where we have IID data, we can drive the excess risk to 0. Okay, so here it says that the excess risk sort of saturates here, which we expect not to be the case all the time. It should, in the worst case, fine, but in a lot of situations, this should not be the case. And I'll go through that. I'll argue that in a minute. Okay. Density ratios are another approach. And this approach actually comes from a particular set of procedures, a particular set of algorithms that tries to just do important sampling to correct the bias. Okay, and they correct the bias using the density, the ratio between the two densities. And here, what's nice is that you can just use unlabeled data to do so, often in these cases. And, but this requires estimating the ratio between densities, and so the type of excess risk they get is, again, something that goes down to 0 plus the estimation error of the ratio, okay? This estimation error can be much larger than this rate because density estimation is a hard problem in general. All right, and so this seems to suggest that it is as hard, transfer is as hard as estimating density ratios, which we know it should, which again, I'll show examples where it should not be the case, okay? All right, so every notion of distance between distributions has been tried. Every notion of discrepancy between distributions, whether it's divergence, scale, whatever you can think about has been tried. And what I'll argue is that all these notions, all these existing notions, are not appropriate for transfer because they were designed for other problems, right? And that what we should be doing here is look at our problem of transfer learning and let the notion of distance come out of the problem itself, rather than trying to use existing notions. The reason, because they tend to be over-pessimistic. A lot of the past work has been able to get a result of the following form. If P and Q are close to each other under whatever chosen notion, then transfer is easy. And that's sort of a sanity check, right? If they are close to each other, transfer is easy. However, the question we're asking is, if they are far from each other, does that mean that transfer is hard? That's what will indicate to us that we are using the right notion. The notion is telling us not only if they are close to each other, transfer is easy, but if they are far from each other, we can expect transfer to be hard. Clear? All right. So let's look here again at this same cartoon. This is a source distribution. This is the target distribution. If we look at total variation or extensions thereof, we can drive total variation and extension thereof to 1/2. If we are in binary classification, driving it to 1/2 means there is no transfer. If I go back here to, if I go back here to the type of risk, then excess risk is bounded by 1/2. There is no transfer, okay? I hope that's clear. So here, this is easy to see. If I look at this region and I look at this region, the difference in mass can be driven close to 1/2. All right. However, this is a simple case where we know that transfer should be easy. If I put a linear classifier here, it will do well here. If I use a tree-based approach, it will do well here. If I use nearest neighbors, it will do well here. Okay? Fine. In fact, metrics, any notion of metrics, whether it's Wasserstein distance, MMD, all those things, any notion of metrics cannot really capture transfer. The reason being that transfer learning is inherently an asymmetric problem. So here, I'm imagining a decision boundary that is here, and P, the source, has very good coverage of the decision boundary. However, the target is concentrated here and does not fully capture the decision boundary. However, if I learn the decision boundary here, I'm going to do well here. But if I switch source and target, I'm trying to transfer now from here to here, I will not do as well. So it's an asymmetric problem, and we should not be trying to use metrics which require symmetry to capture the problem. It will be over-pessimistic. Fine? All right. So what about divergences, like KL-divergence, Rényi divergence, and such? They've been tried because these are asymmetric notions. But we get, again, into situations, for instance, here, that let's imagine that the target distribution is lower dimensional than the source distribution. Then what immediately happens is that KL-divergence and all that blow up. While, again, I can put a linear classifier here and do well on the other side. Okay? So these are not quite the right notions yet either, okay? So next, I'll give some intuition as to the notions we are proposing, okay? And this, again, the initial intuition started in that work with Guillaume Martinet in the non-parametric setting. And this is the main intuition. why do we use the source data in practice? We use the source data and train on the source data because we sort of expect that classifiers that we obtain by minimizing empirical risk on the source data will sort of do well on the target data, right? And so we'll just use that intuition and say, okay, if I have low error on the P, it's going to drive low error on the Q. And that simple intuition, there's tons of ways of capturing it. What I'll propose is a simple way of capturing it. I actually, full disclosure, I don't believe this is the best way to capture it. But this is a way to capture it, what I'm going to present. It's a way to capture it that will start giving us answers. Okay? But a first thing that I'll do is assume, for simplicity, that the best classifier under the source is the same as the best classifier under the target. That allows us to capture this thing much more easily. However, I can remove this at the end. Okay? So here, I'll just say that we'll try to capture this intuition the following way. We let rho, which is our main quantifier of the distance here. We call it the transfer exponent rho. And all it does is essentially say that the excess risk under the target is driven down by the excess risk on the source by this quantity, okay? By this much, that's all. It's a very simple way to just say this. If the excess risk under the source is going down, then the one under the target is going down, and how fast it's going down is captured by this exponent. So, and I'll give examples of this exponent in a minute, so to get a sense of what it's capturing. But in essence, this is just one way. It's an arbitrary way to capture it. The real thing, all we want, is that there is a function of the excess risk under the source that dominates the excess risk under the target. That's really all we want. Okay? Sorry?
Why do we have this intuition again?
Oh, this intuition is simply because why are we using a particular data set? While we know that it's not the right data set and we're training on that data set, it's because we expect that the classifier we're going to get under this data set, if it has low error on this data set, that's all we know, it's likely to give us low error under the target. That's what we hope in practice, right? And I'm just going straight for that intuition. Fine? All right. So we'll see that rho will capture a continuum of easy to hard transfer. In fact, as rho gets larger, we'll see that transfer learning gets harder in at least a minimax sense. Okay? Going back to the earlier problem that I was saying, where if the notion of distance is large, does that mean that transfer is hard? And this way of looking at the problem will capture it. Okay? And if rho is small, transfer is easy. We'll see that in a second. Okay, so first examples of what this exponent means. One point I would like to make is, for the sake of this presentation, for just the sake of this presentation, I'm only paying attention to this part, to the rho. In fact, together, rho and this constant are important. But for simplicity, we'll just pay attention to the exponent. Fine. I'm happy to explain details offline. Right. Okay, so here the exponent, let's try to understand it quickly. So I'm going to simply look at basic examples where y is deterministic, y is given by an h star in the class. Okay, what happened? Okay. Y is given by an h star in the class, and in which case the excess risk just reduces to the mass of the disagreement region between h and h star. Okay? And now let's look at this simple example. Here in this example, Q is uniform. P is also uniform, but on a different support. And this is h star, the decision boundary. This is some ht. Because both are uniform, then the mass of this disagreement region, the ratio of the mass is just a constant. And so we can see that rho is 1. the constant is absorbed, and rho is 1. And however, I can in this exact drawing, the dA discrepancy, the y discrepancy, the dA divergence are all 1/4. In fact, if I pull this out, I can bring them to 1/2. It doesn't matter. Okay. So the key point here is that rho is 1, and it turns out that rho equal to 1 is fast transfer. Means the source data is just as good as using the training data, using the target data. Okay. So here is another case. Here we're back to the case of Q being lower dimensional than P. P is uniform here. Q is uniform on this manifold. We're looking at linear classifiers. For the same reason, if I look at this disagreement region, if I look at the ratio of masses, rho is 1. But I can let by KL, Rainier, and all that blow up. And so this is back to the case where, and all this blow up, and so they have, in that sense, they are very large, yet transfer is easy, as rho is 1, as we'll see. Okay. Here is a case of general rho, taking any value. So the intuition is this. Again, we're back to Q being uniform, but now this is the decision boundary, and P goes down to 0 at the decision boundary at a particular rate. It turns out that how fast it goes to 0 determines rho. Okay? So how fast it vanishes around the decision boundary determines rho. So here is the intuition here. If I sample from such a P as my source, the decision boundary is not observable, easily observable from my sample, because P vanishes around here. I will get mostly samples outside of the decision area, and so my error will be larger than if I sample from Q, which gives a lot of mass to the decision boundary. So that's sort of the intuition. Does that make sense to everyone? And here is a case also where I can show again the asymmetry of transfer. If I flip P and Q, so I'm going to flip it, now Q vanishes around the decision boundary, P is uniform, rho is below 1, which is a case that we call super transfer. It's a case where it turns out that it's better actually to use the source than to use the target for that particular classification problem. Okay? All right, so let's get more formal. We're saying that rho capture is performance limit in a tight sense for transfer. And so before, however, I proceed, I first need to set up one thing. It will turn out that the limits of transfer do not depend just on the distance between distributions, but also depend on how hard the classification problem itself is. And so that will become important in which type of algorithms can do as well as possible in transfer. And so what do we mean by how hard classification is? I'll just use simple cartoons. If I look at this classification problem, it's easier than this one. It should be intuitive to people. Why? Because the decision boundary is very visible here. There is a margin. And the decision boundary is not that visible here. Okay? There is a lot of noise around the decision boundary. And essentially, this type of noise is classically controlled by a so-called Bernstein class condition. You don't need to, you can read it off. It's just saying, how does the excess risk relate to the mass of the disagreement region? You don't need to remember this formula. The only thing is that whenever you see this beta, the beta is controlling how hard the classification problem is. Okay? Beta is between 0 and 1. Once I give the result, you'll see what I mean by beta is controlling how hard the classification problem is. It turns out that this notion of noise turns out to be very important in how well we can do in practice. Okay? All right. So again, we are given labeled source and target data. And this is the main theorem. The main theorem takes this form. Forget the IMSU for now. I'll explain what it is. But we're just saying that the best risk you can get is of this form. It's of the form NP to the 1 over rho. So some term that is some term that comes from the source and a term that comes from the target to minus 1 over 2 minus beta. Recall that beta is between 0 and 1. This is the hardness of the classification problem itself. If beta is 0, we have the hardest classification problem. That's when we get our usual 1 over square root n rate. Okay? If beta is 1, we get faster rate, 1 over n type rate. And this is all that's captured here. Okay? And here, what we get is something that behaves like an essential, an effective sample size from the source, given the distance to the target. All right? This rate is tight in the following sense. What we're saying is that there exists a classifier that attains this rate, and no classifier can beat this rate, in the sense that for any classifier, there exists a distribution with transfer exponent rho such that it cannot do better than this rate. Okay? And how tight is this? It's tight actually for any value of the parameters. And why I'm emphasizing this, often in machine learning, people will give you an upper bound and say, this is tight because there exists a hypothesis class for which it's tight, or there exists a value of rho for which it's tight. We're saying here it's tight for all the values. Okay? I hope that's clear.
So that includes it's tight for, what does it mean that it's, well, this is a supremum over P. So P and Q could be worst case here.
P and Q can be worst case over the class that has Bernstein class condition beta transfer exponent rho.
Got it.
Okay. All right. So benefits of unlabeled data, it turns out that, so these are sort of the questions we asked in the beginning. What is the benefits of unlabeled data? It turns out that here we can show that unlabeled data cannot improve the rate because the lower bound is constructed such that the algorithm has full access to the marginals. It knows the marginals, it knows everything. It can sample as much unlabeled data as it wants. It cannot beat this rate. Okay? This doesn't say that unlabeled data doesn't help in practice. It just says that it only helps up to constant. Okay? Benefits of label Q data. We were asking what is the relative benefit of data from P and data from Q. This is captured in the rate. We get a sharp transition at which all of a sudden the rate is driven down by NQ rather than by NP. Okay? Adaptive sampling, I won't get too much into it for the sake of time. Adaptive sampling is the question I asked earlier. Is there a way to adaptively, if I'm given the cost for sampling from a source and the cost from sampling from a target, is there a way, without knowing rho, beta, any of those things, is there a way to adaptively sample so that I minimize the sampling cost? Right. Now that we have the form of the minimax rate, we can invert it and come up with a notion of optimal cost and then ask those questions. In the paper, we show a particular algorithm that can, in some regimes, achieve an adaptive sampling cost, but we don't know whether it's possible in all regimes. Okay. Lower bound analysis, for the sake of time, I have about, 15, 20 minutes? Okay, so I won't say too much about this. Let me just quickly tell you the key points here is that usually lower bound analysis are constructed in the situation where I'm sampling, where the sample that the learner is observing is from the distribution under which I'm trying to do well. Okay, so now all of a sudden I don't have an IID sample. And so that brings in a bit of complication in adapting usual lower bounding methods. And all I was trying to explain here is how we remove that issue in the analysis. Okay? And how you remove the issue is essentially by looking at tuples of pairs of distributions together and viewing it as one distribution and pulling it through the usual machinery. Okay? All right. The more interesting part is the upper bound. How do we achieve the upper bounds? Because that's starting to tell us which algorithms do well, which algorithms attain these limits, which procedures out there. There are tons of heuristics, tons of procedures out there that do very well in practice, but we don't know in what situations they do well. We don't understand what are the principles that they are capturing, right? And so we're starting to understand a little bit here. And this is where, again, the beta, the notion of the hardness of classification comes into play. So the question I'm asking here is, this is nice, it's a nice rate, but we do not know beta in practice and we do not know rho in practice. So is there a way to adaptively achieve this rate? Adaptively, and all I mean by adaptively is from sample alone. Looking at the sample alone, is there an algorithm that from sample alone achieves this rate or near this, something close to this rate? Okay. And that algorithm is allowed to try to learn row. It's allowed to do whatever it wants. And so what we first show is that in low classification regimes, in low noise regimes, so when the classification problem itself is easy, when beta is 1, then the most naive procedure is nearly minimax optimal up to log terms. This is just ERM, empirical risk minimization, on combining the source and the data and pretending that they are from the same distribution. Something that simple is near minimax optimal if we are in low noise regimes, okay? Soon as we are outside of low noise regimes, then we have to do some type of penalized risk minimization. And here is, and there are various forms of penalized risk minimization that we can show do well. Okay, so here is a simple form: minimize the empirical target risk, subject to the source target risk being small. How small? Not too much bigger than the best in class. And so how much bigger is this delta NP? It's a complicated formula, but the delta NP essentially captures the variance of the error of the classifier H in the source sample. Okay, but it's an empirical variance. Those who are familiar with Rademacher complexity, this is actually an empirical Rademacher complexity term.
So here, if I understand correctly, what you want to do in the bottom algorithm is sort of use P to give you a set of candidate
Exactly.
that is smaller, hopefully, than the original class,
and then train on that.
Train for that.
Exactly. And this is actually one of the heuristics people do in practice. Right? It's very similar to so-called meta-learning or so-called hypothesis transfer. Here, you're not transferring a single hypothesis. You're saying, let me first reduce down to things that do somewhat well, and then train again on the target. And we can show that this is always minimax optimal, up to log terms. Okay? All right, so I'll give a quick summary and now talk about multitask. Multitask was in the title. And multitask turns out to be fairly different from the case of 2, which was surprising to us. Okay, so quick summary, we came up with this notion. For me, it's more of a philosophy of looking at the problem, which captures a more optimistic view of transferability, P2Q. It's starting to reveal general forms of optimal heuristics. In the main paper, we have many more. We consider many more algorithms. Cost-sensitive sampling is possible without knowledge of rho in some regimes. And we can remove H star, this assumption that H star P is equal to H star Q. It adds in an additional term, which is the excess risk of H star P under Q. Okay, we can show that this term cannot be removed fully. Okay, and I can discuss that offline. It cannot be removed fully. However, I do believe that it is still somewhat of a pessimistic term, that in some situations with a lot of structure on the conditional, we should be able to remove it. Okay, or at least attenuate it. All right, so current work, performance limit in multitask. Let me explain what was puzzling to us here. So here in multitask learning, it's nearly the same problem, but now rather than having a single source, I have multiple sources. I have big N sources, okay? And I have my target Q. I have samples from each one of them. I have some samples from Q. And let's imagine I have little n samples from each one of them. I have big N of them. And what was interesting to us is that if we look at all the prior literature on multitask learning, the best rates achievable turned out to be just in terms of a single task, not in terms of the aggregate. Why are we looking at a multiple task? Let's say that I have 100 tasks, 1,000 samples per task. What I'm hoping is that my error rate is driven down by the aggregate sample size, something like 100,000, right? What is shown is that the error rate is driven down by 1,000. 1,000 happens to be 1 over 1,000 or 1 over square root 1,000 happens to be the worst part of the rate. And so we're asking, why is that? That is strange because that goes counter to why we want to do multitask. Okay? So it turns out that there is a big difference between looking at big N as a constant or looking at it as one of our asymptotic variables. And I'll explain that in a second. Okay? So if I really want to understand the effect of big N, it's a different problem. That's the point I'm making. Okay? So here, the setup is fairly similar to before. What we'll try to do is we'll go first to a problem that is very easy. We want to make the problem so easy that for sure, the best rate achievable should be in terms of the aggregate sample size, not in terms of one sample. Okay? And how do we make it easy? We're just going to assume, as before, that the best classifier in each one of the sources is the same as the best classifier under the target. And then we'll relate each source to the target through a transfer exponent rho t. But they all have different transfer exponents. Okay? What we can show is that the best achievable rate is, in fact, in this setting, in terms of an aggregate sample size. Okay? And it takes this strange form. The t here represents a ranking of the task. What ranking of the task? It's the ranking that goes, the first task is the closest to the target. The second is the second closest in terms of rho t's. Okay? And so we show that the minimax rate is a cutoff, and the rho bar t here is whatever the cutoff is, the average transfer exponent for the data set that we aggregated. Okay? The key point is not here. Forget it's a nasty looking rate, but that the rate is indeed in terms of an aggregate sample size. But the point here is that this is an oracle rate. Oracle rate in the sense that the algorithm, whenever you prove a minimax rate, you have to have in the back of your mind that the algorithm knows the class. And what that means is that the algorithm knows the parameters of the distribution, the parameters of interest. If the algorithm knows the parameter of interest, we attain this aggregate rate. But in practice, the algorithms do not know this. And so the question we're asking is, what if I'm looking at a real algorithm that does not know all these parameters? Can we adaptively achieve this rate from sample alone? And the answer will turn out to be no, unless we have some additional information. So adaptive strategies, as n grows, again, if we are in low noise regimes, it turns out that the dumb algorithm, the naive algorithm, ERM, on combined data sets in low noise regimes achieves this rate up to log terms, up to log factors. Okay? Soon as we are outside of beta is equal to 1, so beta equal to 1 is not the most interesting one, so beta not equal to 1, then if we have this information, the ranking information, we don't know the rows, we don't know the actual distances to the target, we just know the ranking of them, which is presumably approximately fine in some practical situations. The way people pick up their data set is because they feel like it's close to the target somehow. If we have the ranking, then we show that there exists a greedy strategy that also attains this rate adaptively without knowing the actual distances up to log terms again. So then that gave us a lot of intuition as to, okay, what about the general case? I don't have the ranking. Beta is not equal to 1. What rate is achievable? This was the surprising fact. It turns out that you can only achieve a rate in terms of a single sample size if you don't have, if beta is not equal to 1 and you don't have the ranking information. Which goes back to explaining why only prior work could only show single sample rates, because they didn't make any strong assumptions. I hope that's sort of clear. And the way we show this is simply by, okay, we saw that, okay, we can get this rate if we have the ranking. So what we did to prove that this is the case is we then forced the algorithm to discover the ranking. So we randomized the problem over the rankings, over all possible rankings, and forced the algorithm to discover the ranking. And that the algorithm does not know the ranking a priori. And so we show that, okay, in that case, there is you cannot beat, no algorithm can beat the single sample rate, even if the distribution allows for a ranking, even if an algorithm that knows the ranking can achieve a much better rate. And so it turns out that there is a gap, an arbitrary gap we can put between an Oracle procedure that knows some information about the class and a procedure that does not know, that doesn't have information about the class. I'll say a point here. The gap between adaptivity and minimaxity is something that statisticians have known for a long time, but often in different situations, the gap tends to be order log n. It's like the Oracle rate, let's say, is square root 1 over n. They can show that an adaptive rate can only be log n over n. So you cannot. So there is usually often a small gap if your algorithm knows nothing. But this is a case where you have an arbitrary gap if the algorithm knows not much about the problem. All right, so I'll stop here. And the main thing I wanted to convey is that this is a very rich problem. It's worth answering questions. And we are really just starting to understand. We are really scratching the surface. There are tons of things in even our way of approaching the problem that is not fully satisfactory yet, right? Even the result I just presented, rather than telling me that we cannot do well, tells me that maybe we need to look at the problem in a different way. Maybe constants are important, right? Because in practice, we do see people do multitask and gain. So what is the source of that gain, right? And so those are the main things I wanted to convey. And thanks a lot again for inviting me. Thank you.
Okay. Hi.
Ashok.
Let's try again. So I just had one clarification about the multitask setting. What is the actual assumption on the row coefficients for the tasks? Like, I'd imagine sort of a very simple thing would be if the average row for all of the p's is somehow not that big, then I could just pick a p at random, right? So what are we
So
looking
to
at here?
construct this, we allowing the row to the worst case row to be large.
Okay.
Right. The worst case row is large, so that the ranking is important. So so you can decide to throw away some of the data set. If beta is large, so there is noise in the problem, and some of the distributions are very far from you, they can throw you off. And we need it far enough with respect to the sample size and with respect to the number of tasks in order to throw you off.
So do you have some way to quantify that? Like,
We quantify the row in this lower bound that throws you off.
but doesn't that give some sort of other thing to try to adapt to, like maybe adapt to that
So
sort of
in the
thing?
paper, we then consider, in the appendix, unfortunately, some other situations similar to what you just said, where we say, okay, what if, in fact, half of the tasks, and half here means in terms of total sample size, half of the tasks have small enough row. Like, what happens in those situations? And it turns out that if I have domination of good tasks, I'm also approximately optimal. So there are tons of remedial situations where we are fine. But without any additional assumption, and that was one of the things we wanted to try to understand, why are people just getting the 1 over little n rate rather than the general rate? Right.
Thanks.
Thank you. Please.
So I guess my question was about what are the kind of categories of relationships what one might consider between P and Q? Because it seems all of the modeling you're talking about is sort of finding situations where, at least roughly speaking, the classifiers that do well on P do well on Q, right? But it seems like a lot of the strategies that have been effective in transfer learning, at least the ones that I think of as getting the most attention, like in translation, for example, what they're doing is they're using P to find a representation that's useful and then kind of retraining some entire part of the model, right? And so those types of relationships would be, from what I
definitely
understand,
not,
like
those type of
terrible
relationships
according
are
to your measure.
definitely not captured here.
Right, right.
Yeah.
So,
and so
are there just like two, or is there like, what is the kind of space of relationships that we should be exploring?
So the key answer that I'll give you is that there are just two that I think about. It's those two. And so this one is the classical one that theoreticians in the area have thought about, right? And at the end of the talk, when I said I don't feel like we are looking at the right things, or we are looking at a complete picture, is actually because of the type of question you just asked. Because in practice, there might be maybe the H's on the P are not doing well at all on the Q. However, there is some structure that is being transferred across. And that actually goes back again to the fact that practitioners are ways ahead of theoreticians, right? And so that's what a lot of practitioners have been looking at, in fact, in meta-learning and such, or even in the way we do transfer with neural networks, where we believe that maybe part of the neural network we've learned is that structure that is transferable across tasks. That has to be captured in a different way than the way we're trying to capture the problem here. We do believe that we can refine these notions of transfer exponents to eventually capture those type of situations by looking at subclasses. But right now, the notion as I presented here don't capture these problems. And that's the next step for us is we need to try and understand those problems where there is, in fact, a structure that is being transferred across, or a structure that gives information across, right? And as to the question of is it just those two, I imagine that the point of saying there is a structure being transferred across, that's actually a very rich family of potential things to look at. Because what is the structure? Is it just some simple linear representation? Is it something much more complicated? Is it some causal information that is being transferred across? And so all those things need to be looked at. And thank you.
You had also, I'm going to guess the answer is maybe not thought about yet, but when you have an algorithm for something you sort of described, sort of like a penalized risk minimization thing, right? That was clearly sort of something I wouldn't actually want to run, right? It's very slow. Do you have any idea about if I could do that efficiently?
So that's actually one of the things I started looking at over this summer is can we implement some of these algorithms? Obviously, the way, let's say, this version of the procedure or the way it's written here, right? The way it's written here. Obviously, we don't know how to minimize empirical risk, empirical 0-1 risk, right? And so can we use surrogates? And if we use surrogates, what are we losing, right? So I'll just tell you high level. We tried using some surrogates. It works fairly well. We cannot prove mathematically that it works well. And I'm asking myself, am I just being a dumb theoretician and not produce a paper on this just because I cannot prove it does as well as I see? But that's sort of the place. But for me, the point is trying to understand why that particular surrogate is doing well. What are the choices of surrogates that we can use to do well here? Is it calibrated surrogate? What should it be? Those are the things I'm still asking myself. But you can easily implement the same thing just using surrogate losses.
Okay.
Is that the answer?
Yeah. I mean, as much as I think there is.
Sorry? Yeah. The only thing I'll say is this, is the delta NP here is need to properly capture the variance of the surrogate in the sample.
Great. There are no other questions. Let's thank Samory again.
Thank you.